This is problem 9-54 out of your book. We're told that we have an ideal diesel engine with air as the working fluid, and we're told to assume constant specific heats at room temperature in this problem. The compression ratio of our engine is 20, so R equals 20, and we're told that at state 1, we have air at 95 kPa and 293. We're also told that the maximum temperature in our cycle is 2200 Kelvin. Alright, so let's go to the next slide. First thing I always recommend doing is drawing the cycle that you're going to be analyzing. So let's draw the PV and the TS diagrams. So first we have our PV diagram, and this is helpful because when you're analyzing the cycle and when you're given information like the compression ratio and the peak temperature, the PV and TS diagrams will help you figure out what states those are at. So let's draw our PV here. It's a little bit lumpy, but let's try that again. Okay. Okay, still a little bit lumpy, but we get the idea. And we can mark our states here. So state 1 is before the compression, and remember, so state 2 here. State 2 is post isentropic compression, so this is S is constant. Oops. Let's label it like this. Okay. Then we have from 2 to 3 up here. That's our isobaric heat addition. Okay, so this guy, isobaric. Then we go from 3 to 4. Here's 4. We label this guy again, S equals constant. Oops, write that a little neater here. So isentropic as opposed to isobaric, P equals constant. Okay. And then we have 4 back to 1, which is isochoric, or volume is constant. Okay, so now looking at this, we can interpret some of the information that we were given in our problem. We were given the compression ratio, R, we're told that's 20, and we know that R, the compression ratio, is Vmax, max, over Vmin. And so we see that Vmax occurs at 1, let's write this here, it occurs at V1 and V4, which are the same, and Vmax occurs at V2. So I'm going to rewrite my compression ratio as V1 over V2, knowing that I could also write this as V4 over V2. Okay, so now I've interpreted a little bit more of my problem. Now let's do the same for the TS diagram. Okay, so now I'm going to draw my TS diagram. Oops, that's really lumpy. And again, these are standard for a given cycle. So if you have a given ideal cycle, these are standard diagrams, although not often quite so lumpy in your book. Let's see, one more try. Okay, slightly improved. Those are supposed to be straight lines. Okay, so let's mark our states 1, 2. So as we expect, S is constant between 1 and 2 because that's an isentropic process. Then we go 2 to 3. This is our isobaric heat addition. And then we go 3 to 4, isentropic. 4 to 1, isochoric. So let's label those again. And again, I like to do this every single time because it helps me interpret the problem and remind myself what's going on between each state. Isobaric. Isentropic. And isochoric. Okay, and so now, again, going back to the problem, we can interpret another piece of information. We're told that the maximum temperature in our cycle is not to exceed 2200 Kelvin. And so we can see that this maximum temperature occurs at state 3. And so we know T3 equals 2200 Kelvin. And so now this is very useful because now we're going to go through and we're going to analyze our cycle to find the things that the problem wants us to find, and we're going to use those pieces of information. Okay, so keep those cycles nearby, and let's go ahead and answer the first part of the problem. So the first thing that we want to know is, what is the thermal efficiency of our cycle? Oops. All right, so in class we derived an expression. Well, we did it for the Otto cycle, but it's okay, it's the same process to derive for the diesel and other cycles, whereby we get net work out, and we compare that with the heat that we have to put in, and that is the thermal efficiency of the cycle. Now we rewrote this for a diesel cycle, just reworking this in terms of Q in, Q out, using isentropic relations. And what we ended up getting was an expression that is this. So this is our expression. Again, no mystery where this comes from. This comes from this equation up above, but just being reworked. Now, let's look at the different components of this equation and let's see what we have. So, we have in here a compression ratio, R. We have that. That's good. We have K, which is the ratio of Cp to Cv, or ratio of our specific heats. So K equals Cp. Over Cv, which we can get from property tables. I find this to be, let me rewrite all of that. So K equals Cp over Cv, which I find to be 1.4 at 300 Kelvin from the property tables in our book. Okay, so I'm going to use that value. Let me write that a little neater here. CV 1.4. Okay, so now I have my K, I have my R, but what's the last thing I need? It is RC, which is our cutoff ratio. And remember, that is the ratio of the volume after combustion to the volume before combustion, or heat addition step. So V3 over V2. So what we realized pretty quickly is that we don't know V3 and V2 yet, so we need to find the states at 2 and 3, if you can read that little note down there. Okay, so find the states at 2 and 3. All right, so let's do that now, and then we'll be able to find our thermal efficiency. Okay, so state 2, let's find state 2 first. And as we talked about in class, there's usually a pretty standard approach to these problems, which is to start from the state that you know and start marching forward. State 1, for example, we know, so start finding state 2, state 3, and if you need, state 4. And then you can find pretty much anything you need to know about the cycle. So let's find state 2. What do we know? We know that the process from 1 to 2 is isentropic. So we're going to use that to our advantage to find state 2. So we're going to use the isentropic ideal gas relations, T2 over T1 equals V1 over V2. to the k minus 1, which we can rearrange to be T2 equals T1 V1 over V2 to the k minus 1. Now we know what T1 is. It's we're given, let's see, 293 Kelvin. We know our V1 over V2 because we just analyzed that. That is our compression ratio, so we know that. So let's go ahead and plug in and find T2 is 293 Kelvin times our compression ratio, 20 over 1, raised to the k minus 1, which is going to be 0.4. And we find that T2 is 971 Kelvin. Now let's do the same thing to find P2. We're going to use another one of the isentropic ideal gas relations. And remember, these come from our TDS equations. Our TDS equation was integrated, and then we substitute in for using things we know about the ideal gas law. And so we end up with these isentropic ideal gas relations. So specifically, they're for isentropic processes and for ideal gases. So V1 over V2, doing the same thing, rearranging. Plugging in, we find P2 is 95 kPa times 20 over 1 to the 1.4, which is 6,300 kPa. Okay, so now we know T2 and we know P2. And what I like to do, even though we don't have space to do it here, is I like to go back to my PV and my TS diagrams, and I like to either write them right on the diagram, or I like to keep a little tabulation next to it of what my states are as I find them. Okay, so state 3 is the next thing we need. 2 to 3 is isobaric, so we're going to use what we know about the process between the states to find the next state. So 2 to 3 is isobaric. So what do we know? Right away, we know P3 equals P2, which equals 6,300 kPa. We know that because it's isobaric, it's the same pressure. Then we also know T3, because we analyzed that property table, or that TS diagram, we know that T3 equals T max, which equals 2,200 Kelvin. All right, so we know now P3 and P2. All right, so we know these guys. So good. So now we're almost there. So now we can calculate V3 and V2, our specific volumes at these states, using the ideal gas law. And we need those, just as a reminder, because we need to find our cutoff ratio. All right, so V3 is going to equal RT3 over molecular weight P3. Okay, I'm just going to plug in 8.314, and always watch the property, units on that ideal gas constant. So this guy is kPa, meters cubed, over kmol Kelvin, times 2,200 Kelvin over 29 kilograms per kilomole, the molecular weight of air, times 6,300 100 kPa. Okay, so when I calculate that, I get V3 equals 0.100 meter cubed per kilogram. I'm going to do that. Just do the same thing for V2, using again the ideal gas law here, and I get 0.044 meters cubed per kilogram. All right, so then I can go ahead and calculate my cutoff ratio, which, a reminder, is V3 over V2, and I get 2.3. Okay, and so this was the last piece of critical information that I needed to calculate my thermal efficiency. So we're ready to do that. So on to the next slide. Let's just write that out. I'm going to plug in those numbers. Okay, so I've plugged in just rewrite that guy. Plugged in all those values that I found, and I get 0.634 for my thermal efficiency, or 63.4%. Okay. Just a reminder, a couple things, that the thermal efficiency always has to be between 0 and 1. This is true for all of your cycles, and then again you can express that in terms of a percentage by multiplying it by 100% or 100. Okay, so let's go to part B of this problem. Part B, we want to find a mean effective pressure. Oops. And just a reminder what the mean effective pressure is. That is the pressure, one constant pressure, that if this were to be exerted through the cycle between Vmax and Vmin, it would produce, let's see if I can write and talk here, it would produce the same work that the cycle produces, the same net work out. So, mean effective pressure. Okay, so it's one single pressure that, when acting through the volume, Vmax, Vmin, produces the same net work as the actual cycle does. All right, and it's a nice, quick, easy way of comparing cycles. Okay, so the MEP we define as the net work out over Vmax, Vmax minus Vmin. Okay, and if you look at that expression, rearranged, it would be W net out, work net out is P times delta V. You see right away that that's what it says. Okay, so we know a couple things here. We know Vmax equals V1. We can find that using our ideal gas. Let's see if I can rewrite that. Using our ideal gas law. And we find that to be, because we know T1 and P1, we can find that to be 0.884 meters cubed per kilogram. And we know Vmin already. That's V2. We've already calculated that. 0.044 meters cubed per kilogram. Okay, so we found that previously. All right, so now what do we need? We need the net work out. Okay, so this is what we need to find. Now, we remember that we talked about, for cycles, the net work out equals Q in minus Q out. And that's just from a simple energy balance. Because we know that our final and initial states are the same, the change in energy of the system is 0 at when a cycle is completed. And so what we're left with from our energy balance is just that the net work out equals Q in minus Q out. Okay, a couple other things we can identify here. So let's switch colors here. Q in. If we go back to our PV and TS diagrams, we see it's Q between 2 to 3. And Q out is going to be the negative, the inverse of Q 4 to 1. And that's because, remember, Q from our energy balances, these have signs associated with them. When we identify them as Q in, Q out, these do not have signs, they're always positive. Okay, so the Q out is going to be the negative of Q in, Q 4 to 1. Okay, so these are the things we need to find, so let's go ahead and do that. All right, so let's focus on Q2 to 3 first. So we're going to use an energy balance. On our system for the process 2 to 3. So we can write that a little neater. Process 2 to 3. Okay. So remember, we're modeling this as a closed system. So we can write this as change in U, internal energy, CV dt for an ideal gas is going to be Q minus W, where W is, reminder, our boundary work. Okay. So let's rewrite Q 2 to 3. It's going to equal CV dt plus integral PDV between 2 and 3. Now we can simplify this a little bit because, reminder, this is an isobaric process, which makes this pretty nice and easy. So the integral from 2 to 3 of PDV just equals P times V3 minus V2. Okay. So really nice and quickly, we can calculate our boundary work as being, and remember this is all on a per unit mass basis, so these should all be lowercase. Our boundary work is 6,300 kPa times 0.100 minus 0.0, that's 0.044 meter cubed per kilogram, and we end up with our boundary work is 353 kilojoules per kilogram. Okay. Now, I also find that my CV, I can find this from the property tables, is 0.718. Kilojoules per kilogram Kelvin. And so now let's go ahead on the next slide and plug all those numbers in and calculate our Q2 to 3. So Q2 to 3 is 0.718 kilojoules per kilogram Kelvin times 2200 Kelvin minus 971 Kelvin, that's the delta T, plus boundary work, which is that 353 kilojoules per kilogram that we calculated, and so we get 1,235 kilojoules per kilogram. Okay, so now let's do the same thing. We're going to do, so this is our first value that we needed. So now let's do an energy balance on 4 to 1, which is our heat rejection step, to find our other Q. So let's write that energy balance. Delta U is CV delta T, which equals Q minus W, so same thing as before. Now this time we have an isochoric process, so this guy, the W goes away because it's isochoric. Because PDV, dV is 0, there's no boundary work being done. Okay, so that makes it nice and simple, except we need to find, okay, so let's rewrite this. Delta U is CV, is CV T1 minus T4. And so what do we need to find here? We need to find T4. So let's do that right now. Okay, so we need to find, let's just write, okay, so let's find T4. Okay, so we know, again, we're going to use what we know about the processes to kind of march our way forward. 3 to 4 is isentropic. So So we're going to go back to those ideal gas relations for isentropic processes. T4, over T3 is V3 over V4 raised to the K minus 1. We know that we know V4 equals V. Ooh, a little messy here. We know V4 equals V1, which equals 0.884 meters cubed per kilogram. We found that before. Okay. So we know our V4, we already know our V3 because we found that before, and we know our T3. So we know everything we need to know. We're going to say T4 equals 2200 Kelvin times 0.100 over 0.884 raised to the 0.4, which equals 920 Kelvin. Now we can plug that into our Q. Q 4 to 1 equals 0.718 kilojoules per kilogram Kelvin times 293, which is our T1, minus 920 Kelvin that we just found equals negative 450 kilojoules per kilogram. Now we can plug in, we can find our net work out. Oops. So that's net. Let's rewrite this whole thing. We can find our net work out as our work in. Again, that sign doesn't change because it's positive. So in is positive already. But then we want to subtract the work out, which, reminder, already has a negative sign associated with it, but we want the absolute value of this. So minus 450 kilojoules per kilogram. Okay? And when we calculate that, we end up with 785 kilojoules per kilogram net work out. Now, next slide, we can finally calculate our mean effective pressure, which equals 785 kilojoules per kilogram over dV, 0.884, our V max, minus 0.044, our V min, that's meters cubed per kilogram, specific volumes, and we end up with 934 kPa. And that's it. So a couple of things to take away. Number one, I suggest always drawing those PV and TS diagrams. They'll really help you to visualize. And then generally the solution process is to, based on what you need to know, march your way forward through the states, find the subsequent state based on the state you know, and then you'll be able to solve most things in the problem.